My name is Nazim. My colleagues and I will share with you some technical information that we recently announced. If you haven't paid attention to the announcement, what we announced was we will provide a reconfigurable acceleration stack that's targeted for key compute applications, especially machine learning, inference, video transcoding, and video analytics. These are our initial offerings. Over time, we plan to offer other applications that are more suitable for what FPGAs can be used at. But let me first start with the agenda. I'll briefly introduce the topic, talk about what is Reconfigurable Acceleration Stack, and then my colleagues here will talk more details about each of the applications and go into more depth. And in the end, we'll talk about what we're doing with the future in terms of acceleration with our CCIX announcements that we made a few months ago, and Gaurav will talk about that. So why is acceleration important? So the primary reason is computing needs are going up tremendously. Things like natural language processing, moving to 4K and 8K video processing, video analytics. So all of this is driving computing needs tremendously. And the CPUs just can't keep up with it. And so what FPGAs can provide is the acceleration capability to be offloaded from the CPU. The other important thing is, in addition to computing needs that FPGAs provide, it also can solve the bottlenecks in storage and network acceleration. And Ravi will talk about that in the last part of our agenda on acceleration. So what does it mean? What does acceleration mean for FPGAs? So the way we do acceleration is we offload applications that run on a CPU onto an FPGA. And we do this by plugging in a FPGA card. It's a PCI Express card. It's similar to, you can think of it as a GPU card. We have effectively an FPGA card that offloads key applications that run on a CPU onto an FPGA and providing basically better TCO for data center customers. So there's been a lot of the industry has been talking about FPGAs and acceleration, and we have a few anecdotes here. The first one, Microsoft has been pioneering in this area, and they have demonstrated very clearly that FPGAs is very valuable in the data center for applications like search and network acceleration. And they have deployed a broad set of, in the data center, a broad set of applications that can use the FPGAs, and they have a wide deployment in the data center. We recently announced with Baidu that Baidu is also using FPGAs in the data center for machine learning, and this is something that we have jointly, they're using a Xilinx FPGA for that. In addition, if you look at even DeFi Tech is another company that announced in Hot Chips a mechanism to accelerate inference, machine learning inference with FPGA significantly. So these are all examples of where FPGAs are getting more mainstreamed in the use. And what we are going to talk about today is what are the applications we are going after in terms of accelerating in the data center. So why are these guys using FPGAs? Fundamentally, what FPGAs provide is very compelling performance. So if you look at the metrics here, we have collected benchmark data on various applications. And you can see compute applications as well as storage and network. If you look at the compute accelerations, we have anywhere from 11x to 40x performance per watt compared to a CPU in terms of improvement. And this is actually very significant. And this is what is compelling people to use FPGAs in the data center. In addition, if you look at storage, and especially compression or virtual switch and networking, these are also things that CPUs can't keep up with, especially when we get to 25 gig, 40 gig, and 100 gig traffic. And we are able to accelerate these traffic also with an FPGA. And this is another reason why data center customers are using FPGA. Now, the reason for not people quickly moving to FPGA generally is because FPGAs can be a challenge to it can be a challenge to migrate applications from CPU to FPGA. So what we have enabled is to provide them the entire stack to make it easy for them to use the FPGA. And if you look at this, traditionally we would offer an FPGA as a silicon, but what we have taken is we are actually offering the entire stack, and that's our key announcement that we made, which is in addition to just the FPGA, we are providing a platform. If you look at the bottom of the stack, there is a developer board, and you can also deploy it, which provides a PCI Express card, which provides a mechanism for hardware acceleration. But in addition to that, we provide libraries that are suited for specific applications, and I'll talk about that in the next slide, for things like CNN and video transcoding. And these libraries enable you to, and these libraries are optimized for FPGA, and they make it easy for you to migrate the application from CPU to FPGA. And in addition to providing the libraries, we connect it to some common industry standard frameworks. So if you have a cafe-like framework from running machine learning on a CPU, we can provide an easy transition from that to transitioning to an FPGA. So we connect most of these library and applications to some industry standard frameworks. In addition to providing the frameworks, we also have an OpenStack framework that enables provisioning and virtualization, and you can run these applications similar to what you would run on a CPU, except it will run on FPGA. So fundamentally, what we're doing with the stack is making FPGAs very easy to use, and it's transparent to the user in terms of migrating an application from a CPU to an FPGA. Now, let me talk one level deeper here, and this is and my colleagues will go through in depth on each one of these. If you look at the machine learning stack, for example, you will see at the bottom we provide the accelerators, and then these accelerators consist of basically FPGA and a board that plugs into PCI Express. Then we have some development tools that enable this in terms of runtime to use these FPGAs. On top of that, we provide libraries for machine learning, for example, DNN and GEM, and connect to the framework cafe, which runs on top of OpenStack. So I'll let first Ashish come up here, and he's our machine learning expert, and he'll talk about what we have done in machine learning inference. Ashish, thank you.
Thank you, Nazim, and I am really very excited to be here and share the work we are doing at Xilinx to enable the machine learning stack. And here I will just give you a preview. This is a pretty broad area, and I will just point out on some of the salient points which we are focusing on. And hopefully this can start a discussion and we can engage more people in this endeavor. So at a very broad level, we all know that deep learning is a buzzword. Whenever you talk about machine learning, people talk of deep learning. And this is no longer just a buzzword. We do interact with deep learning technologies on our day-to-day basis. Our Gmail folder will do spam filters. We talk to our cell phones, and they translate voice to text. And just the other day, my friend and his son was telling him his best friend is Amazon Alexa. And he asked him why, because it helped him do the math problem. He's a first grader. So from that point of view, we are seeing that it is available everywhere. So on one hand, it is kind of bringing an application we didn't think of earlier, or we thought of these are not possible. But on the other hand, the compute requirement for doing this is pretty steep. And when you deploy on a large scale, as Nazim had already said, the efficiency of doing it is very important. So just at a broad level, whenever you think of deep learning, people also use the term artificial neural network or deep neural network in conjunction with that. I'm not going to go deeper into it. But fundamentally, there are two distinct phases of deep learning. One is where you train a network or you train a given model for a given problem or a set of problems. And then you deploy in a large scale on a cloud server or a hyperscale server. And really what you see is learning is very important, but it is kind of an effort which is one time, or it is done on a background. It is typically done on a cluster of CPUs and GPUs. And FPGAs can surely be deployed on that, but the more interesting thing is when you deploy it to be used for masses, that is where the problem becomes very interesting. And one of the key things, what was conventionally thought, and this is one of the key takeaway we want to make is, conventionally it was thought is the arithmetic precision with which you are going to train the network, is it the same precision you will require for the inference? So for example, floating point 32 is something which is used heavily in training, and there are reasons for it. There are debates about it, is whether it is needed or not. But industry has standardized on that. But when it comes to inference, the most recent research has really shown that you can do a pretty good inference with a reasonable amount of accuracy with 8 bits or 16-bit integers. And this is one of the key takeaways. So what you do is, whenever you go to the lower precision level, there are a few things which happen. One is the energy efficiency. So how does energy efficiency basically, how the lower bit width translate to energy efficiency? So people have done some benchmarks, and what you can do is, for a given amount of energy, you can do 10x more computation when you go from floating point 32 to floating integer 8. And I think a lot of computer scientists are here and they will understand what I'm really saying. The other advantage you have is, as you reduce the bit width, you are basically, your energy to interact with the memory also goes down. And easily it will translate to the number of bits you are using to go back and forth with your memory. That's the 4x kind of improvement you get. And on top of all of this, what you really get is, you can compress your models, which basically reduces your bandwidth in terms of deploying on a larger scale. So what we really think at Xilinx is, Xilinx FPGA in particular, and I will show you in the next slide, are ideally suited for inference-oriented deployment of some of these machine learning applications. And that is why inference is a focus area. Now, what drives this? And I'm not going to go into detail. And what we really have is a very inference-friendly DSP architecture. Now, here it goes into a little bit details. But really what this DSP can do is, it can do a single bit multiply accumulate in one cycle, which is basically the heart of most of the machine learning inference. And on the other hand, what you can really do as well is, you can really pack 2 8-bit operations and do 2 8-bit multiply accumulate in one cycle. And this is pretty unique for our DSP block. And how it translates into application, if some of you in the audience are very familiar with the convolutional neural network, you can really see in the bottom, we show 2 examples where you can basically go from an input feature map to output feature map transformation. And if you go down to the 8-bit, you can really compute 2 outputs in one cycle versus 2 output in one together versus 1 output at a time. So what it really does is, you are getting all the advantage of going down to 16 bits of a fixed point arithmetic, but on top of it, the Xilinx architecture allows you to effectively double, it's not really double, but for ease of explanation, effectively double your compute performance. And it gives you the kind of compute density, when you deploy some of this machine learning on a larger scale, I think it will be pretty interesting to see. So we have written a white paper on how we can do some of these optimizations, and it is available on our website. And I will encourage you guys to go and see that. Now finally, it boils down to, as Nazim said, is machine learning is fine, your FPGAs can do things, but all my deployment is based on software. I use Caffe, maybe I use TensorFlow, maybe I use my own thing, right? And one of the things we are trying to really do is abstract out the FPGA as much as possible. Now, it's not that everything we can do together, and if you see what was said in Nazim's earlier slide is, we are giving a benchmark stack, where we really show you how we are doing machine learning. And this benchmark stack is ready to go. You can use it as it is. And the key things what we are doing are these boxes in the red you are seeing is what we are really applying. So we are providing a one-to-one translation for some of the key machine learning functions like Con2D, or you do maxpool, or you want to do ReLU. And as well as, if you want to do fully connected layer, there is a one-to-one translation. And there is a thin layer we are doing, which we call it at XDNN, and it really basically orchestrates your data movement between your FPGA as well as your host. So it's a kind of, when you are looking at a framework which is public domain, and some of them will port it and show you how it is done, but if you have your own framework, there will be enough examples where you can basically focus on the software aspect, what you are good at, rather than focusing on FPGA's program. So that is one of the key things we want to do. This doesn't take away your ability to optimize your FPGA function, but the thing is that you get you started, and you can see whatever we are talking about in a very quick way. So I think at a very high level, these are the few points we want to basically, we want to showcase, and there is a demo running in our booth, and I'm encouraging you to go and see it. So machine learning is one particular part of data analytics. There is lots and lots of data which is basically sitting in the standard SQL databases or no SQL databases. And this is the kind of data where people are mining this data to do what typically known as unsupervised learning or some kind of different kind of analytics they want to do. And Baidu, who is one of the premium partner, recently published a paper in Hot Chips, Hot Chips 2016, where they demonstrated that by implementing some of the key functions, and more specifically, these are the non-indexed SQL functions, where you are basically scanning a large set of data in FPGA and doing it in FPGA, you can get up to 25x acceleration compared to the CPU. So we are working closely with many customers, and what we have done is one of the requests they give us is, tell us how do you integrate with the FPGA. And to basically address that request, what we have really done is these two boxes down here in the red. What we have basically deployed is a data mover library. You can hook up to MySQL, you can hook up to PostgreSQL, and you can quickly get going. And some of the key functions like send, scan, compare, filter, and they are massively parallelized on the FPGA. And on the right-hand side, what we did is we took this particular framework and implemented it on the FPGA, and we did see a really good result, which basically translated into 34x compute efficiency. This is one of the standard business analytics. TPCH is one of the standard business analytics benchmark which people use in the SQL world. So in summary, I think our journey has started. We are at a very firm footing in terms of how we are enabling machine learning and data analytics on FPGA. And these are some of the framework we will be sharing with you people as we go forward. And this is a kind of a preview. And with this, I will hand it over to Johan, who will talk about video and video acceleration.
All right. Thank you, Ashish. My name is Johan. I will be talking about another workload that we believe indeed is very well suited to be accelerated on FPGAs as well. I'm the video architect in Xilinx, basically driving these solutions into this space. And I will show you through a few slides today that FPGAs can really accelerate this workload and have a much higher compute density compared to traditional solutions. So if you look at a transcode use case that typically is being deployed in a data center, and transcoding, what people may not realize is that all devices that are connected have displays or cameras like your phones, for example, or TVs or media players, etc. Once you stream something through YouTube Live or Facebook Live or some of these new applications, that compressed stream ends up somewhere in a data center, and the data center actually touches that stream. It's being decompressed. There's typically video processing being done on that content, maybe even analytics to detect what kind of content is in there, and it's being re-encoded one or multiple times depending on the use case that you're basically involved in. And to date, most of that workload is going through typical x86 solutions running on software. And if you look at a typical use case like this, there's quite a number of processing that needs to happen to actually transcode it. And really for video, if you look at video, it's really where the compute-intensive resources are going, especially the video encode. If you look at a typical use case, it will take about 70% of your resources on any architecture, let's say a CPU. And we believe that with an FPGA, we can accelerate that in a way that it gives a much higher compute density compared to CPUs. And I'll guide you through that to see how we do that and what the value really is for an FPGA. So with this slide, I try to illustrate basically how compute can scale in a data center. If you look at video workloads, let's say up to about a year or a few years ago, where most of the video that was being streamed through servers was offline. Like for example, if you stream a movie, the encode part of that streaming can be done offline. So you really have no extreme need to stack, let's say, a bunch of servers to do that real time, but you can even do that in the off hours. For that, an x86, you could argue that that is an architecture that is reasonably suitable for that. But with all these new workloads that are coming, let's say in the last year, online gaming, Facebook Live, YouTube Live, I already mentioned them. There's really this need to do all these things real time and preferably with very low latency, especially when it's interactive. And all these workloads go through these servers. So you really have to stack a bunch of x86 servers to get through this real-time capability. And we know that with FPGAs as accelerators, we basically need one FPGA to do a real live stream at the same quality levels that you target basically for these applications. So let's talk about that. So basically, from an encoder point of view, so really if you look at video encoding, not all encoders are created equally, let's say. I mean, the encoder really determines the quality of the stream that it generates in terms of the amount of bits that it needs to reach a certain, let's say, PSNR or picture quality level. And since the compressed stream typically is pushed on a network, which typically is the bottleneck as well, the fewer amount of bits that you use for the higher amount of quality, the better that encoder is and the better suited it is for these applications. So this shows a graph of a number of profiles for a very commonly used encoder in basically a data center environment. It's an open source encoder which is called X265, which basically has profiles that run at a reasonable speed for a certain resolution to a very slow speed. Of course, the very slow speed gives the highest quality, and that's really the quality that we, from an encoder, are really targeting in this space. And you can see at this very low frame rate, it's going to be quite challenging to get that to run in real time and architecturally scale that. So, and we have solutions on our FPGAs that basically match these quality targets, but give you a throughput of real time, 60 frames per second, or even scale it higher up if you use one of our, let's say, higher performing devices. So to illustrate this a little bit differently, basically this is a rate distortion curve, and this is really the first thing that let's say our customers would like to understand in terms of our solutions, in terms of our accelerators. And this rate distortion curve shows basically the quality of that particular encoder, first certain bit rates, and gives you a certain PSNR in this case. I'm showing this here basically to compare, let's say, this X265 very slow profile, which gives you a typical quality level, which is very high for HEVC, with a solution that we have running on our own FPGAs, very similar quality, visually very much the same, also from a PSNR point of view. But if you look at the throughput on the FPGA, you can run this at 60 frames per second. And in software, you're talking about a few frames per second. So that's really the differentiation and the value proposition, I think, that we can offer for these kind of workloads. Okay, this is already my last slide. So I wanted to put this also in a benchmark, basically in this table, where it's a real-life example again, a little bit different flavor encoder, an encoder that runs on a certain Intel CPU at a throughput of 3 frames per second for a resolution of 1920 by 1080 resolution. That device typically consumes about 120 watt. And if you then look at the compute efficiency in terms of frames per second per watt, this produces about 1/40th frame per second per watt for this configuration. If you look at our own implementation on a Xilinx accelerated FPGA, in this case a VU190, we achieve again 60 frames per second at a device power of about 60 watt, and then the compute efficiency here is about 1 frame per second per watt. And if you look at the difference, it's really a 40x increase in compute efficiency. And that's really a big gain of an FPGA compared to a traditional x86 solution. So that's what I wanted to leave it with. I'm going to hand it over to Ravi. He's going to talk about networking and storage.
Hi, my name is Ravi, and I'm responsible for data center solutions at Xilinx. So my colleagues Ashish and Johan talked about compute acceleration, but one of the key differentiations for FPGA that we believe is also networking and storage, and that's one of the key strengths. So obviously, I'm going to provide a quick overview of there's a ton of work we're doing internally as well as with our customers in terms of enabling networking and storage acceleration. So in addition, we already talked about how we are developing a SDAccel virtualized infrastructure to enable compute acceleration kernels with compute workloads. But in addition to that, what FPGAs are well suited for are networking offload or virtualized network functions, whether it be VPNs, firewalls, custom protocol offloads, or security, as well as storage workloads. And some of the functions that you can map to the FPGAs are essentially leveraging high-end networking, including 100 gig network interfaces, as well as more intensive, protocol-intensive workloads, such as whether it be vSwitch offload, crypto offload, as well as QoS and custom protocol offloads. So from that point of view, I think, and finally, of course, from a storage point of view, FPGAs again are pretty well suited. These include all the way up to RDMA, which is RDMA or Converged Ethernet offloads. So from that point of view, we think we have the ideal converged accelerator. And the reason we think that is FPGAs today are well equipped, not only from having hundreds of thousands to millions of lookup tables, thousands of DSPs, which work very well for compute, but in addition to that, we have dozens of very high-speed transceivers. So today, Xilinx FPGAs support 25 gigabit per second interfaces. We also have very high-end integrated networking IP. You can get the latest Ethernet IP with all the data center bridging features, as well as timestamping and other things that are needed in the data center. The other key thing that has evolved is we have augmented block RAM with ultra RAM. So today you can get FPGAs with hundreds of megabits of embedded RAM, and we're also announced where we are augmenting this with high bandwidth memory. Our future products are going to come with high bandwidth memory. So what those enable you to do is to create custom optimal memory hierarchies that are suited for your workload, whether it be compute or networking or storage. And so that is essentially leading to some of the gains, whether we see in machine learning or in video or networking or storage. And finally, we do have very advanced host interfaces. You can get Xilinx FPGAs today that support early versions of PCI Express Gen 4. And going forward, Gaurav Singh is going to talk about our roadmap for C6, which is the industry consortium driving a cache coherent interface for accelerators. And this is some of the work that we are doing. So our goal is to, as data center networking speeds evolve from 1 gig to 10 gig, today we think they're going to move from 40 gig and quickly to 100 gig. We think CPUs are going to run out of steam processing 100 gig workloads. So our aim is to enable 100 gig virtualized network functions. And the key thing that we can provide is not only offload functionality, but also inline acceleration or bump in the wire acceleration. So your networking traffic does not have to leave the FPGA and make the round trip up to the CPU and back. So that's, we think, is a key flexibility that FPGAs provide. So most of you, so security, I want to talk a little bit about security. Security is actually one of the key strengths for FPGAs. Most of you probably already heard about Microsoft deploying their SmartNIC across their entire data center. And one of the key workloads that they're driving is a 40 gigabit per second crypto offload, DTLS crypto offload. So we are actually internally as well working and with customers in terms of accelerating, for example, 100 gig IPsec offload. And there actually we are leveraging our experience with the 400 gig MaxX solution that we have in production today. And in addition to that, the other thing is essentially virtual switch offload. At 10 gigabit per second, maybe CPUs essentially, it's very very intensive for CPUs to handle at that speed, but going to 40 gig and 100 gig, we think you need to offload this to some accelerator. We think FPGAs are a good fit there. So we are actually working on enabling 100 gig OVS offload, and there we are actually leveraging the SDNet compiler that we have today. It's PX is a precursor to P4, so we support PX, and we are also supporting P4. So this compiler enables you to generate your own custom programmable packet processing pipelines to support whatever network processing that you want to do. And finally, last but not the least, we realized that, hey, you can create all these kernels in the FPGA, but without the stack to hook it up to the application, it's going to be difficult to deploy that. So that's why actually we are developing networking stacks using, whether it be with standardized Linux kernels or DPDK, to enable you to develop these applications. Finally, I'll talk about storage actually. So one of the key things, as you all know, is flash is becoming pervasive in the data center. And there essentially NVMe over Fabric is becoming the fabric of choice for scaling. And hence, actually Xilinx has already developed an NVMe over Fabric solution to offload some of this workload from the CPU. And we are actually actively developing a Rocky protocol offload as well. And the reason we think that offloading this to the FPGA helps you is obviously for these workloads you're going to reduce the utilization of CPU. But the second more important thing is this allows you to do inline acceleration for storage, as well as enable certain new compute near storage paradigms. And just to show you, actually, for the NVMe over Fabric, we benchmarked that against a CPU. So we are able to get similar throughput to a CPU, but reduce the CPU utilization significantly. In addition to that, what this is enabling us, and obviously we're working with some customers, is error correction, compression, security, which you can do inline, which would not be possible if this was done in the CPU. So finally, I'll actually pass it to Gaurav. He'll talk about our C6 architecture.
Thanks, Ravi. Well, thanks all for coming. That's pretty fantastic performance already, right? But if you see, there's a common theme here, right? When you look at FPGA acceleration. And the common theme is that about data movement, right? At the end of the day, you have to get data into the FPGA, do lots of interesting things with that data, and then write it out, right? So that brings to question, what is that interface by which the data is moving in and out of the FPGA, right? That interface now becomes important. Characteristics of that interface in terms of latency, in terms of bandwidth, in terms of power efficiency become very important, right? So just as an introduction, my name is Gaurav Singh. I run the Silicon Architecture Group at Xilinx. And we've also been involved in some of the consortia activities in driving some of the standards that will make those interfaces better, because that is of key importance to us, and also to other accelerators like GPUs and NICs and so on. So I'll talk about C6, or the Cache Coherent Interconnect for Accelerators, as we call it. And so what basically started off about a little over a year ago, when we were looking at the interface and saying, well, you know what, we're seeing this fantastic performance already, right? But as we look at the future, the type of data movement where the bandwidth is going up, there's a lot more interaction between the processor and the accelerator, meaning that rather than it being a fire and forget, where you DMA a whole bunch of data to the accelerator, there's a lot more interaction that happens between the processor and the accelerator, right? So we looked at it and said, well, maybe there's a way we can improve the interface of today, right? And that's how C6 was born. So what C6 is, it's an open standard with backing from multiple processor vendors and also accelerator vendors. So we're unique in the sense that we've got members who are part of the x86 processor architecture, power, as well as ARM. And fundamentally what we're doing is we're trying to make the accelerators become fully capable devices in the processor ecosystem. And what I mean by that is, Nazim mentioned the thing of usability, right? We're doing a lot of things in making that sure that our stack allows FPGAs to become very easy to use. But wouldn't it be nice if giving a workload to an FPGA could be as simple as passing a pointer over, right? None of the pinning of buffers in memory, no setting up complex DMAs, right? Not having to process the data and then DMA it back to processor's memory. You could process it right off the FPGA's memory, and the FPGA's memory is fully visible to the processor's memory, right? So then the processors and the FPGA have a common address space, right? They can both participate with the system memory, irrespective of whether the system memory is, whether it's connected to the FPGA or of the processor, right? And so from that point of view, then the acceleration becomes as simple as taking a pointer, giving it to the FPGA, and you're done, right? So that's what C6 is trying to do. And so in order to get to that level of ease of use, we have enabled coherency across that link, right? So effectively, you've got the coherency that is really part of the processor subsystem is now extended to a heterogeneous device. And so that pretty much is what C6 is. Now, in choosing the pins and choosing some of the physical layers for C6, we could have invented our own, and certainly that was an option. But what we decided to do was to leverage what already exists, right? And the de facto standard today is PCI Express, right? PCI Express Gen 4 is at 16 gigabits per second, but all processors have it, all accelerators have it. So we said, well, and if you look at a lot of these dense server systems like half-U boards, there isn't a lot of mechanical real estate to add another connector, right? Also, when you look at the kind of applications that we spoke about, there is the offline compute applications, but we also have the inline networking and storage acceleration applications where you really want to be on that main interface that is getting into the processor, which is PCI Express, right? So basically what we've done is we use the same interface as PCI Express. However, we do a few things to it, like using a different channel altogether so that we're not bogged down by the limitations of PCI Express. And so you get a completely clean interface where we can use our own packetization, so we can get really good efficiency on that link. And the other thing we've done is we have increased the speeds to 25 gigabits per second. You'll probably see there's a disconnect between the I/O technology that's available today. We've got 25 gig that we're shipping today. We've already sampled 56 gig I/O, right? Whereas PCI Express is still the 16. So you can see there's a big disparity between what the I/O technology is capable of and where the standards is. And C6 is attempting to close that gap, right? So we are at 25 gigabits per second today. Now, if you look at the topologies that we can enable, of course, the most interesting and probably the most common use case will really be a processor and an accelerator directly connected over C6. But there are cases where, we spoke about this new class of memory that's coming up with the storage class memory. There's lots of interest in enabling direct connection to that storage class memory to the processor itself or in any device. And basically what that allows you to do is obviously it gives you the random accessibility. You can do load stores to that memory, but it also happens to be non-volatile. The third use case is by reusing the PCIe electricals. What we can do is we can use standard off-the-shelf switches to enable a fan-out to a larger set of accelerators if we so choose to do so. But we're also enabling a direct connection, so you can have a processor here connected to multiple FPGAs, and we could even have a two-piece system where you have another processor there connected to this FPGA, and all of those devices share the same address space. So now data can move seamlessly between the memory, and that is of particular interest for some of the new applications that are coming out where the amount of data that needs to be processed is shrinking, right? If you have a large, and traditionally we've had large bulk data that was farmed out to the FPGA, right? But by enabling a system like this, what you can do is you can enable small snippets of code, right? You can have processing of very sparse data structures, right? Where you really don't have to a priori decide which portion of that big database you want to farm out to the FPGA. You can just pass a pointer, and the FPGA will go grab the memory wherever it is, right? So that enables a whole new class of applications that haven't yet been farmed out. So in terms of the, we started off with about, earlier this year, we started off with 7 companies. So far, we've seen lots of enthusiasm in the industry, and so we've got, I think, close to about 26 members today. We are adding more, and the members are from all, from the processor space. We have members who are part of the accelerators. We have members who are part of the IP group who are developing IP for C6 to make it easier for silicon vendors to integrate that IP. We have software vendors who are looking at how to enable C6 in the operating system and make that piece of it available. We have connector vendors who are designing and looking at, well, when we look at 25 gig and now we're looking beyond 25 gig to higher speeds, what type of connectors should we use for the servers? And then we also have some of the OEMs and some of the end customers who are actually going to end up using it, right? So I believe that we've got a fairly, full-fledged ecosystem that's sort of building around C6, and we're really excited about that. So the status where what we have is, so we started earlier this year, and we already have released one of the specification, and that is serving as a target for a lot of the silicon starts. So we will have multiple companies implementing it. We announced a product last week, which will have C6 in it. And we will expect to have some silicon systems with both processors and accelerators, multiple accelerators in the 2018 timeframe. So with that, I think that's my last slide. But we're really excited about this, and we hope that some of the performance numbers that you've seen, the next time we are here with C6, we can show you even better performance.
Okay, as you guys all saw, the value proposition of FPGA is very compelling. The reconfigurability enables us to have very compelling performance in a breadth of applications, not only in compute that you saw with machine learning, video transcoding, and database analytics, but in addition, storage and networking as well. So that's a very compelling value we provide through reconfigurability. And the other thing that we are making it is making it easy to use by providing the entire stack all the way from the hardware layer all the way up to the software layer all the way to OpenStack in terms of making it easy for you to transition your applications that run on a CPU to an FPGA. With that, we will open it up for questions. When do you guys come up, stand up here, and we'll open it for any questions you guys have.